You know that glass of water you just poured? Think about this for a second. There could be a whole unseen world swirling in there. Microscopic particles.
Hmm.
Today, we're diving into that world specifically. Microplastics and nanoplastics and, well, they're a surprising presence in our drinking water.
Yeah, it's a topic that's really getting a lot of attention now, and it should be.
Hmm.
These tiny plastic bits, they're everywhere, really, a result of how much plastic we use,
Hmm.
and understanding what they might do to us, to our health, and, the environment. It's becoming critical.
Right.
It even ties into the big global goals, like the UN's Sustainable Development Goal for clean drinking water. So
Hmm.
it's a major issue.
Absolutely. And to really get our heads around what's happening, we've dug into some pretty substantial research, a big systematic review.
A really comprehensive one, yeah. They pulled together findings from 26 different water treatment plants,
26? Wow. Across how many countries?
12 countries. And they didn't just glance at a few studies, they analyzed 103 different pieces of research,
Okay, 103.
which boils down to 54 actual published articles. So a huge amount of data synthesized.
That's
Yeah.
that's massive. So what's our mission with this deep dive then?
Well, the goal is to really unpack how these treatment plants are actually coping with these tiny plastics right now. We want to look at how effective the different methods are, what works, what maybe doesn't work so well,
Hmm.
and importantly, where we still need more research. Where are the gaps in our knowledge?
Okay, let's start right at the beginning. The journey of these plastics. Where do they even come from in the raw water?
Well, the sources are pretty much linked to our plastic habits. Think packaging, clothes, shedding fibers, bits breaking off larger items out in the environment.
Right, just daily life, basically.
Exactly. It fragments, gets washed into rivers, lakes, groundwater, the
Mhm.
sources for our drinking water. And interestingly, wastewater treatment plants were initially thought of as a big source entering the environment.
Yeah, makes sense.
But the process within those plants, the churning and filtering, can actually break down larger plastics, especially fibers, into even smaller pieces.
Oh, right. So the treatment itself might be creating smaller problems.
Potentially, yes. These smaller fragments can then get passed on to the drinking water treatment stage. It's a key point. A process meant to clean things up might inadvertently be making some pollutants harder to catch later on because they're smaller.
That's, yeah, that's something to think about.
Definitely. And another thing, while we're focusing more on what goes into the drinking water plants,
Uh-huh.
there's actually surprisingly little research looking specifically at what happens inside the pipes, the distribution system that brings the treated water to your tap.
Hmm.
That's a bit of a blind spot we'll come back to.
Okay, good point. So let's talk about what they are finding in the raw water coming into the plants. What kind of numbers are we looking at?
The range is, well, it's incredibly wide. The review found concentrations anywhere from about half a particle per liter, 0.55 to be precise, right up to, get this, 6,614 particles per liter.
6,000
Per liter.
per liter, yeah. And one study even measured it by mass, finding 93.2 micrograms per cubic meter. It just shows some water sources are relatively clean, others are dealing with a huge load.
That variation is stark. What about the types of plastic? Is it mostly one kind or?
It's the usual suspects, really,
Yeah.
reflecting what we produce the most globally. Polyethylene, PE think bags and films, polypropylene, PP containers,
That's
packaging.
yogurt pots and stuff.
Exactly. Then PET, your plastic bottles,
Mhm.
polystyrene, PS styrofoam, polyamide, PA nylons, and PVC used in pipes and construction.
So basically, the plastics we see everywhere are the ones ending up in the water.
Pretty much, yes. It directly mirrors global production.
And size-wise, are we talking mostly nanoplastics from the get-go or bigger pieces?
The sizes found in the influent, the incoming water, range from 1 micrometer up to 5,000 micrometers, which is 5 millimeters.
Yeah.
But a very common range seems to be between 50 and 224 micrometers. Shape-wise, fibers are the most common thing they see, followed by fragments.
Fibers, like from clothes. That's a major suspected source, yes. Laundry lint is a big contributor. As for color, there's less data, and weathering can change the appearance anyway, so it's harder to trace origins that way.
Okay, so that's the raw water picture. How different is it when we look at tap water?
Well, microplastics are found in tap water. Concentrations up to 440 particles per liter have been reported.
Still quite a range, but lower than that 6,000 peak in raw water.
Generally lower, yes. The types of plastic are often similar: PP, PE, PS, PET, PVC. But here's the twist we mentioned earlier.
The pipes.
Exactly. There's a real possibility that the distribution system itself is adding some plastics back in after treatment. The common size found in tap water tends to be slightly larger, often in the 83 to 400 micrometer range.
Huh.
Larger. Why would that be?
It's not entirely clear yet. Maybe aggregation, maybe different types of sources within the pipes. Again, fragments and fibers are common. It tells us the treatment plants are doing something, but maybe not everything, and new sources might pop up later. Right. So the plants are definitely removing some, but it's not a perfect barrier. Let's get into how effective these treatments actually are. The review splits it into stages.
That's right. Two main categories got roughly equal attention in the studies reviewed: coagulation-flocculation-sedimentation, or CFS,
CFS, okay.
and filtration. But let's start even earlier with the very first step: screening.
Right, the basic sieve at the start.
Exactly. It catches the big stuff, leaves, twigs, larger debris, and it does okay with larger microplastics, say 500 micrometers and up. Pretty good for 300, 500 too.
But the smaller stuff.
Yeah, below 300 micrometers, its removal ability really drops off. The suggestion is pretty straightforward. Use screens with smaller holes.
Makes sense. Prevent them getting further into the system. Okay, now onto that CFS process, coagulation, flocculation, sedimentation. Sounds complex.
It is a bit technical, but it's a core part of water treatment. Basically, you add chemicals, coagulants that make tiny suspended particles, including some microplastics, unstable. They lose their charge.
So they start repelling each other.
Precisely. Then flocculation is just gentle mixing to encourage these particles to bump into each other and stick together, forming larger, heavier clumps called flocks.
Oh, okay.
And then sedimentation is simply letting these heavier flocks settle down to the bottom so they can be removed. It's designed to get rid of general cloudiness, turbidity.
But it catches microplastics, too.
It can, yes.
Yeah.
But how well it works for microplastics, that's where it gets complicated. The effectiveness really varies.
How much variation are we talking?
A lot. Lab studies show removal anywhere from just 1% up to 100%. But in actual treatment plants, the range is even wilder, from negative 356%.
Negative? How is that even possible?
Fragmentation, the mixing involved, the shear forces can actually break down larger microplastics, especially those fibers we talked about, into smaller pieces.
So you end up with more particles than you started with, just smaller ones.
Exactly. So a process meant to remove can sometimes, paradoxically, increase the number of tiny particles. It's a really important finding.
Wow. That's quite counterintuitive. What about the chemicals used, the coagulants? Does that make a difference?
It does. Traditional ones are inorganic salts, like aluminum sulfate or synthetic polymers, but there's growing interest in natural coagulants.
Natural? Like what?
Things derived from starch or chitosan that comes from shrimp shells, or even cellulose and lignin from plants. They could be more environmentally friendly options.
Are they effective?
They show promise, definitely. Some studies report good removal, especially maybe in combination with the traditional ones. They work by neutralizing the plastic surface charge and also kind of building bridges between particles.
Okay.
But there are hurdles, extracting them efficiently, getting enough raw material, and how well they work can depend a lot on the specific water quality.
And the dose. Does using more coagulant always mean better removal?
You'd think so, but it's not always clear-cut. The optimal dose really depends on the type of plastic, the coagulant, the water chemistry. It's complex. Some research suggests higher doses help if charge neutralization isn't the main thing happening. Adding other polymers like PM can sometimes boost efficiency too.
What about the plastics themselves? Does it matter if it's P versus PVC or big versus small?
Well, most studies looked at the common ones: PE, PS, PVC, PET. Surprisingly, though, the review found little strong evidence that particle size makes a huge difference in CFS removal, at least in the range tested, which was 0.1 to 5,000 micrometers.
Really? I'd have thought smaller would be harder to catch.
You'd think, but the data doesn't clearly show a massive effect for CFS specifically. One gap, though, is polypropylene. PP, not much research on its removal via CFS.
Interesting. And shape. Fibers versus fragments.
Shape is thought to be important, yeah. Affects surface area, how it interacts. But again, most lab studies use nice convenient spheres or fragments. Very little work has been done on fibers in CFS, just one study mentioned.
And you mentioned weathered plastics might behave differently, like plastics that have been out in the sun and water for a while.
That's a crucial point. Most lab stuff uses pristine, brand new plastic. But real-world plastic is weathered. One study did compare and found weathered PE was removed better than pristine PE.
Why would that be?
Probably because weathering roughens the surface, increases the area, and creates new chemical groups on the surface from oxidation. These give the coagulants more to grab onto.
Makes sense. And the water itself. Does muddy water help or hinder? What about pH?
Absolutely, water characteristics matter. Higher turbidity, meaning more suspended stuff already in the water, can actually help MP removal in CFS.
Oh,
The microplastics can get kind of swept up and trapped within the larger flocks that form to remove that general turbidity. pH is also key. It affects the surface charge of both the plastic and the coagulant, influencing how well they stick together. The ideal pH varies. And natural organic matter, NOM stuff like humic acids from decaying plants that can have mixed effects. Sometimes it helps, sometimes it hinders, depending on the coagulant and how much NOM there is.
okay, so CFS is definitely complex, lots of variables, even that risk of making things smaller. What about dissolved air flotation? DAF, you mentioned that as an alternative.
Right, DAF. It's particularly useful for plastics that are less dense than water and want to float anyway.
How does it work?
You dissolve air into the water under pressure, then release the pressure. Tiny bubbles form and attach to particles, including microplastics, lifting them to the surface. Then you just skim them off.
Like foam flotation.
Pretty much. And the review notes that if you add coagulants first, a process sometimes called posi-DAF, it can potentially get near 100% removal for MPs bigger than 15 micrometers.
Okay.
But there's just not a lot of research specifically on DAF for microplastics in drinking water treatment yet. Shows promise, but needs more study.
Okay. Now, all this stuff being removed, the flocks from CFS, the scum from DAF, it has to go somewhere. It ends up in the sludge, right?
Exactly. Water treatment sludge, WTS, becomes a sink for these captured microplastics. And the concentrations found there are, again, highly variable, from basically none detected up to a massive 86,000 particles per gram of dry sludge reported in one UK study.
86,000 per gram. That's intense.
It is. The common plastics found in sludge are PE, PET, and PP. A German study looked closely at one plant's sludge. They found mostly PE, sizes mainly 50-500 micrometers, mostly fragments. Interestingly, the number of MPs in the sludge wasn't significantly different from the raw water, suggesting the plant was effectively trapping them there.
So the sludge is concentrating them.
Yes. Another study in Thailand found lower levels but concentrated in a smaller size range. A Spanish study found lots of fibers in their sludge, and they actually saw a link. Higher fiber content in the sludge correlated with better removal from the final water.
That makes sense.
It does, but it all points to a big issue.
Okay.
What do we do with this contaminated sludge, especially if people want to use it as fertilizer or something? We need better sludge management plans that account for microplastics.
Definitely a downstream problem that needs tackling. Okay, let's move to filtration, the other major removal category. Conventional filters for sand, gravel, activated carbon.
Right, conventional filtration. It's basically passing the water through layers of media sand, maybe anthracite coal, activated carbon to physically strain out remaining particles.
How well does that work for microplastics?
Particle size is really important here, though the results are a bit mixed across studies. Some report very high removal, even up to 100%, especially if it comes after CFS. But others show it's less effective for smaller particles, like maybe 10, 20 micrometers, and it can struggle with microfibers smaller than 45 micrometers. Generally, it seems pretty good for MPs bigger than 100 micrometers.
Oh, what about the really tiny stuff, nanoplastics? Can sand filters catch those?
Research suggests slow sand filtration can be quite good, especially once biofilms, layers of microbes develop on the sand grains.
Biofilms help.
Yes, they seem to add an extra sticky layer that helps trap nanoparticles. Flow rate and filter depth also matter. Granular activated carbon, GAC, often performs even better than sand for NPs.
Why GA?
It's more porous, has a huge internal surface area, so it doesn't just filter, it also absorbs particles onto its surface. And adding coagulants before sand filtration can also significantly boost nanoplastic removal.
So these conventional filters can be effective, but there are nuances. The review mentions some challenges, too.
Yeah, predicting performance in real-world plants isn't always straightforward. One big study found sand filtration didn't play a huge role compared to CFS and GSE in their specific plants. But other recent work really highlights sand filtration as crucial, sometimes removing up to 99% early on. So context matters. There's also the worry that friction within the filter might break some MPs down further.
Fragmentation again.
Potentially. And fibers seem harder to remove this way than granular particles. Plus, smaller MPs can stick really tightly to the filter media, making it harder to clean the filters effectively through backwashing. And sudden changes in flow, turbulence, could dislodge trapped particles.
Lots of things to juggle. Okay, what about the more high-tech end of filtration? Membrane technology. Microfiltration, ultrafiltration, reverse osmosis.
Right. Microfiltration, MF, Uses membranes with pores typically 0.1 to 1 micrometer wide. Many studies show it achieves near-complete MP removal.
Sounds great.
It is, but efficiency can drop over time. Cleaning the membranes can stress them, they age, you might get tiny ruptures. Still, MF can catch smaller MPs, maybe around 100 micrometers on average, that conventional plants might miss.
But you said near complete. Does some still get through?
Interestingly, yes. Some studies have found MPs in the water after MF, even when the MPs were supposedly larger than the membrane pores.
Squeezing through.
That's one theory, maybe flexible particles deform. Or maybe there are occasional defects, slightly larger pathways on the membrane. It's not fully understood. Then you have ultrafiltration,
Yeah.
UF.
Even smaller pores.
Much smaller, 1 to 100 nanometers. So UF offers very high separation efficiency. It can potentially replace CFS and conventional filtration, maybe even disinfection sometimes.
Was it designed for microplastics?
Not originally, no. It was mainly aimed at removing natural organic matter, NOM, but it's very effective at removing MPs, especially if you use coagulation before it. Membrane properties matter too, like how water-repelling it is, its charge. And just like sand filters, biofilms can form on UF membranes, sometimes incorporating MPs, which affects performance.
Okay. And the finest level, reverse osmosis, RO.
Yes, RO membranes are designed to remove dissolved salts, tiny molecules, so they can definitely remove microplastics, even nanoplastics.
So why isn't everyone just using RO?
Well, it's mainly used for desalination, making fresh water from salt water. There's less research on it specifically for MP removal in standard drinking water treatment. Plus, MPs could actually clog up or foul the delicate RO membranes.
Oh.
So you'd need really good pre-treatment before the RO stage, like CFS or maybe MF or UF first. We are seeing more combined RUF systems, especially in desalination.
Okay, so physical removal is key, but what about biological processes or disinfection? Do they play a role with plastics?
Biological treatment relies on microbes potentially breaking down plastics, biodegradation, or sticking to them, biosorption. Lab studies show biodegradation is possible, but its effectiveness in real plants is still being researched.
So maybe not a primary removal method yet.
Probably not on its own. One study found some biological tanks actually increased granular MP concentration. Biofiltration, though, where biofilms grow on filter media like GAC, turning it into biological activated carbon, or BAC.
Like the slow sand filters.
Exactly. That seems more effective. It combines filtering and biosorption. BAC can remove a good chunk of smaller granular MPs, but interestingly, it might slightly increase fibrous MPs in the output, possibly due to
Fragmentation.
That's the suspicion. Biofilms forming on the MPs themselves can also make them easier to remove later by CFS. So combining biological and physical-chemical methods seems the way forward there.
And disinfection. Chlorine, ozone, UV light. Do they adapt the plastics?
Generally, disinfection as a pretreatment doesn't remove MPs. Using oxidants like ozone before treatment might change the plastic surface slightly, but it doesn't seem to hugely impact later CFS or filtration removal. Pre-ozonation before biological treatment might help microbes break them down, though.
What about ozone on its own?
Not great for removal. In fact, it can often increase the number of small MPs, 1 to 20 micrometers, probably by weakening and fragmenting larger ones. How much fragmentation depends on the ozone dose and contact time.
So another potential source of smaller particles.
It seems so. One study found ozone didn't fragment nanoplastics, but did change their surface charge. Combining ozone with GAC filtration did show better removal of small MPs and fibers, though.
And chlorine, the most common disinfectant.
Chlorination has shown some reduction in MP numbers in a couple of studies, up to 28% or even 71%. High doses or long contact times can also alter the plastic's physical properties.
And UV light.
UV, especially combined with hydrogen peroxide, UVH2O2, seems to promote fragmentation too. It alters the plastics, increases the count of smaller particles, and the total particle number overall.
So disinfection isn't really a removal step for MPs. It might even make the problem trickier by creating smaller fragments.
That seems to be the current picture, yes. We still lack a really comprehensive understanding of what exactly happens to MPs during disinfection.
Okay, this treatment journey is complex. But you mentioned earlier that the story doesn't end when the water leaves the plant. The distribution system, the pipes, might be adding plastics.
That's the growing concern, yes. This huge network of pipes, valves, pumps. It's designed to deliver clean water, but the system itself could be a source.
Wow.
Through pipe corrosion, pipes made of PE, PVC, PP, even old cast iron can degrade. Abrasion of fittings, often made of polyamide, nylon. Epoxy resin linings in tanks or pipes could potentially shed particles, and biofilms growing inside pipes might trap and later release MPs or even grow on them.
So the infrastructure itself could be shedding plastic.
The evidence is pointing that way. A Barcelona study found MPs in the distribution system similar to those leaving the plant, but weirdly, no PE plastic, even though they had PE pipes. Maybe the age of the pipes mattered.
Did other studies look at age?
A Swedish study actually found pipe age didn't seem to significantly impact the MP load, so maybe it's more complex. The Barcelona study also found no clear link between MP levels and how far the water traveled from the plant. A Thai study pointed fingers at accessories fittings, connectors made of various plastics, and another study looked at the scale built up inside old, burst metal pipes.
What did they find in the pipe scale?
Significant amounts of MPs, mostly small, less than 100 micrometers, mostly fragments. PVC was the dominant type, then PE, PP, nylon. It shows MPs definitely get trapped and accumulate in the system over time.
So they could be released later.
Exactly. Changes in water pressure or flow could dislodge them. Plus, you could get atmospheric dust entering open reservoirs. MPs can also stick to pipe scale and then get released. Some initial lab tests even showed old PE pipes could release fibers and fragments, though they weren't found in the final tap water in that specific case.
So it's clear we need more research on the pipes themselves as a source.
Absolutely. It's a critical piece of the puzzle to understand what's actually coming out of our taps.
Which brings us right there. What are we finding in tap water globally?
Well, we know MPs are there, but getting a clear global picture is hard because everyone uses slightly different methods for finding and counting them. Makes comparisons tricky.
Right. But what do the studies included in the review show?
There are findings from various places. In China, results were mixed. One study found tap water MP levels similar to the treated water leaving the plant, but with more PVC, possibly from household plumbing.
Could be.
Another tiny study found higher MP levels in tap water than the plant outlet, but a third found lower levels, suggesting maybe MPs were sticking to pipes in the system, so it varies.
What about elsewhere?
A multi-country study found PVC in tap water, mostly fragments, diverse plastic types with PS being commonest. They suggested air or the pipes as sources. The Barcelona study found plastics consistent with the treatment plant output, like PP and PA, but also PTFE, likely from plumber's tape, and silicone, maybe from sampling gear. Again, no PE from the PE pipes detected in the tap water there.
So contamination can happen right at the sampling point, too.
Potentially, yes. A Belgian study found average MP levels weren't significantly different between the plant outlet and taps, with PP and PT common. And a German study found levels in most homes were very low, barely above lab background levels, and one tap had none detected at all.
Okay, so summing up tap water findings. It sounds like, generally, treatment plants do remove most MPs.
That seems fair to say, yes.
But some still get through. And where those remaining MPs in tap water come from, whether it's residual from the plant, the main distribution pipes, your home's plumbing, or even the air, is still not entirely clear.
That's a good summary. The major sources after treatment are uncertain and probably differ quite a bit from place to place, depending on the local setup.
This has been, well, a really deep dive. Just as promised. So much to consider. If we had to boil it down, what are the main takeaways for listeners?
Okay, key points. 1, microplastics are present pretty much globally throughout the whole water treatment and delivery process. 2, our current treatment plants can remove a lot of them, but how much varies hugely. It depends on the tech, the plastic type, the water. It's not foolproof. 3, the distribution system, the pipes getting water to you, can itself be a source of microplastics. That's a big factor. And 4, we really need standardized ways to measure these things so we can compare results properly and get a clearer picture worldwide.
So looking forward, where's the hope? What are the promising directions?
Well, there's definitely potential to optimize the treatments we already have, like CFS, making them work better for plastics. And exploring advanced tech like ultrafiltration and reverse osmosis more widely seems crucial. Maybe integrating those advanced physical methods with biological treatments could be a good path too, but we still have big challenges. Managing that contaminated sludge is one.
Yeah, that sounds like a major headache.
And really understanding and then figuring out how to minimize contamination from the distribution systems. That's another huge task.
Yeah, it certainly leaves us with a lot to think about. And maybe here's a final thought for you, the listener. Given how much plastic is just everywhere, what's our role in this as consumers, as manufacturers? How much responsibility do we have to cut down plastic pollution at the source before it even gets near a river or a treatment plant.
Mm-hmm.
If we could reduce the load going in, it would certainly help those plants out.
Yeah.
What other questions does this raise for you about what might be unseen in your own glass of water?